So, hello everyone. Today we have Marieke and Beest from Simon Center, and she is going to tell us about monopole scattering and generalized symmetries. Please
Thanks a lot, Laksha. Yeah, thank you. So I'm very happy to be here, and I'd like to thank the organizers very much for inviting me to speak in this really interesting seminar series. I hope I can live up to it. So I am going to be talking about this paper that I wrote together with Philip Boyle-Smith and Diego Del Mastro and Soa Kumagotsky and David Tong. And it's about monopole scattering and generalized symmetries. But I'm afraid it's going to be just at least 20 minutes before I really get to any monopoles, because first I actually want to discuss a simplified model which contains all the important features of this monopole scattering problem, but where it's not modeled by the existence of a gauge symmetry. So we'll get to the Kalin-Rubakov effect and this mystery of scattering with Took lines and gauge theories soon enough, but let me first start with a simplified setup and discuss the problem here. Okay, so I'm going to discuss the model that's called the 3-4-5-0 model. Also, please do let me know if my writing becomes illegible at any point, because it tends to get sloppy as I progress. Okay, the 3-4-5-0 model. And this is a model simply of in 1 + 1D of a set of free fermions which are charged under a global U1. Okay, so basically in this model we just have, we have two left-moving fermions, and we're going to be calling these psi3 and psi4. And the label here refers to the charge under the global U1. So we have a left-moving fermion of charge 3, one of charge 4, and then we also have two right-moving fermions. I'm going to give them tildes to indicate that they move to the right, and they're going to be psi5 and psi0. Okay, so that's it. That's basically the model. And the reason why the charges have been chosen as they have is because this set of charges gives an anomaly free symmetry, and which is of course just because 3 squared plus 4 squared equals 5 squared plus 0 squared. And furthermore, so I also have this completely uncharged fermion, which doesn't really play any role except for the fact that it makes sure that the gravitational anomaly vanishes as well. So we have the same number of left movers as right movers. Okay, so that means that these symmetries are anomaly free. And that is a necessary condition for the existence of a conformal U1 preserving boundary. Okay, so we want to put into this theory a boundary here that creates a localized interaction between the left movers and the right movers. So this is conformal. Okay, so there's a puzzle in this very, very simple theory. And the puzzle is as follows. Move this up a little bit. So if I throw a 3 into the boundary, how can it scatter? So how can psi3, same question for psi4, of course, but let's just focus on one of them. How can psi3 scatter off the boundary? Okay, so basically the only thing I've required, so what happens if I throw in psi3? So the only thing I've required here is that I have these left movers and right movers. So I have this chiral theory. There's a conformal boundary which preserves the global U1. Okay, and it's been shown that you can write down a boundary like this. So if I throw the 3 into this boundary, since it preserves the symmetry, the thing that comes out better also have charge 3, right? But if I write down the Fock space, which is just, of the outgoing fermions, which is just linear combinations of psi 5 and psi 0, of course, there is no charge 3 state in this Fock space. So it appears that we have a problem. Now, if I insist, regardless, on this U1 conservation, so I insist on U1 conservation, that tells me that if I throw in the charge 3, I would have to get out something like this: 3/5, and then the charged fermion plus whichever number of the fermion that's uncharged, not fixed by this symmetry. But what does this mean, right? So I basically told you, okay, if I have everything necessary to write down this U1 conserving boundary, but if I throw in the 3, the only thing that could possibly come out that's consistent with these symmetries is some fractional excitation. So it's some fractional fermion. Or a fermion with a fractional occupation, something with a fractional occupation number in this Fock space. So at the very best, I think I owe you an explanation for what that is. And at worst, this is telling us that there's no consistent thing you can even write down that comes out. So it seems inconsistent. But it turns out that there is a resolution to this problem. And the resolution that I'm going to give today, and which is also the proposal, which is connected to the proposal for the monopole scattering experiment, is that we haven't included the entire Fock space of the theory. So we need to include the twisted sectors. So spoiler, the answer lies with including the twisted sectors. Okay. So let's be completely concrete. I will consider a boundary state that's slightly more symmetric. So consider a boundary. There we go. Consider a boundary that preserves U1 times U1 prime. So two different U1s, and the charges are given here. So we have two different U1s, and the charges of the first one are just these 3, 4, 5, 0, like we had before. And the charges of the second U1 have been chosen such that it doesn't have any anomaly itself, and there are no mixed anomalies either with the first U1. Right? So everything here is again non-anomalous. So now, because we have as much symmetry as we have degrees of freedom, this scattering is going to be completely fixed by the symmetry. So we can write down, let's say I throw in a 3. Then the thing that has to come out is 3/5 of the psi 5 plus 4/5 of, I'm still going to be calling these I'm still going to be labeling the fermions by the charges under the first U1, but now we have introduced the second U1 as well, and that means that the scattering is completely fixed. And this is the answer. Okay, so let's try to take that seriously for a moment, but in order to give an interpretation for what these fractional numbers could mean, it's useful to bosonize the theory. So we're going to bosonize.
Sorry, can I ask you a question?
Yeah, absolutely.
How do you implement concretely these boundary conditions, this boundary state with the explicit boundary condition on fields? I mean, this is a quadratic theory, right? So the boundary condition could be implemented like writing explicit boundary condition on the fermions.
Right. Yeah. I mean, so you can completely classify, well, you can completely classify all the boundary states. And for each boundary state, there's going to be some, literal boundary condition on the fermion field such that, there's an interaction term that's associated to this particular boundary state.
So something really like that, you take a fermion and you put it equal to some fixed fermion on a boundary.
Yeah. So you can actually, yeah, exactly. You can actually take a left mover and say at the boundary, it is equal to some linear combination of the right movers. Yeah. And you can either write that down as a localized interaction, or you can just literally write it down as a boundary condition that connects the left movers to the right movers. Yeah.
And when you say that a certain boundary condition preserves a certain amount of symmetry, means that the fermion that you're putting equal are uncharged with respect to the symmetry. I'm trying to understand
it doesn't necessarily mean that it's uncharged. It means that this boundary condition that you're putting, where you're saying, okay, some left mover is equal to some linear combination of the right movers, is if these linear combinations are chosen such that a certain symmetry is always preserved. They're going to be such that the symmetry is always preserved. Yeah.
I see, because you have both left and right. I see. Thank you.
Thank you.
And these are conformal boundary conditions. So basically what you're doing is you're gluing the Virasoro left to the Virasoro right, and you're writing the Virasoro in terms of the fermions, and you solve that problem, right? That's basically.
Yeah, precisely. Yeah. So, I mean, that's why I'm saying you can think of it equivalently as writing down an interaction term between left movers and right movers, which only has support at r equals 0, right? I think that's an equivalent way of stating it. Yeah. Okay. So we were going to bosonize these fermions.
Sorry, can I also ask a question?
Yeah,
are
of course.
there mixed anomalies between the two you want?
Shouldn't be.
Okay.
I mean, okay, I can try to convince you. So essentially, the anomalies are just, U1 squared anomalies. So you can just, play around with the numbers in this, and you'll just see that you always have the charge squared of the left movers equals the charge squared of the right movers. In the case of, you either have 3 squared plus 4 squared equals 5 squared, or you have that in both the cases, right, with some minus signs. And then when you take the mixed thing, you have 3 by 4 times 3 by 4 minus 3 by 4 equals 5 times 0 plus 5 times 0. Anyway, it just vanishes on the other side.
All right, thank you.
Yeah. Okay. So let's bosonize a set of free compact bosons. So there's a map modulo the gauging of a set 2, which is not going to play a role here, which maps psi to a vertex operator in terms of this compact boson X, and equivalently for the right movers. And then their correlation functions match. Okay, so then we can write down the scattering. If we translate the above, we just get that we're throwing in this vertex operator, and the thing we're getting out is 3/5. So the 5 plus I and this. Right. So the outstate is some fractional vertex operator. And fractional vertex operators have correlation functions with integral vertex operators that have branch cuts. So the correlators have branch cuts. And what that means is, as we cross these branch cuts, there's going to be implemented some phase on the vertex operator. And essentially, this is defining for us a symmetry defect in the theory, right? So it's a line, or it's a cut, so to speak, where when you cross it, you gain some phase. So it defines symmetry defect. And therefore, we can actually interpret this fractional vertex operator as a twist operator. Meaning that we should see these fractional fermions, so to speak, as actually not being localized excitations, but rather being twisted excitations that live at the endpoint of some defect. All right? So this is the interpretation, where the defect here, call it T. So that means instead of throwing in a 3 and getting out some fractional fermion, whatever that means, we're seeing that what comes out is in fact not a local operator, but rather we throw in a fermion and we get out a defect with something with some excitation living at the end of it. Okay? And we can figure out the action of this defect of this topological line. So the action of the topological line, T, on the local operators. So they're going to be looking like this, 5, 0, and so on and so forth. So that is measured by the monodromy. Right? So we can figure out which symmetry this is by literally just looking at the correlation functions and moving the integral vertex operator around the twist operator once and see which phase it picks up. Okay? And what we find is that this symmetry is a Z5 with these charges for the fermions. So the left movers are completely uncharged. This is a chiral defect, only moving to the right, and it acts on the right movers with charges 3 and 4. Now, crucially, this Z5 sits inside U1 times U1 prime, which means that this topological line, it's guaranteed that it can end topologically at the boundary. And that it has conserved charges associated with it. Of course it does, because it sits inside the group that's already conserved. So in general, what we find in this 3450 model is I throw in psi3 or psi4 or some linear combination. And in general, I will get an out state which lives in the twisted sector. The twisted sector of, in the twisted sector of a C5. Okay, so this is the bosonized story, so to speak. Let's check that this also works out in the fermionic picture and how it works out precisely. So by the state operator correspondence, the spectrum of operators living at the endpoint here of this line is isomorphic to the S1 Hilbert space defined here with an action of the line on it. Okay, so we have a spectrum of operators at the end of the line is isomorphic, the S1 Hilbert space twisted by the line. by the line action. So what that means is I have a certain non-trivial boundary condition that if I take some psi and move it around the circle once, it picks up a phase. Okay, where the QI here are these guys. And the K is for this Hilbert space twisted by T to the K. There we go. And the 5 is, of course, because in this particular model that we're working with, we found that the relevant line operator is a D5. Okay. So in order to work out this scattering experiment, it's all about conserving charge and getting out an out state that's consistent with this charge conservation. And we want to see that, in fact, we can get something that's not a fractional fermion, but something that lives in the twisted Hilbert space that can solve this problem, right? So we need to find a state in the twisted Hilbert space which is consistent with these conservation laws. So the states that live in this Hilbert space at the end of the line operator are going to obviously carry charge. And let's see. And basically, each excited state is just going to carry the charge that's associated to whichever fermion operator I'm acting with. But the vacuum state itself is likewise going to carry charge. So that's the non-trivial computation that we need to do. We need to figure out what charge does the vacuum at the end of this line carry? What does it contribute? Okay, so again, we're going to let T be the generator. So let T be the generator. Of this C5. And we're going to write T to the K as the vacuum. At the end of T to the K, right? So then we can build a Fock space and write an arbitrary state simply like this. Where A and B are defined modulo 5. And in the future, and also in the paper, we use a simplified notation. We just write it like this. But what we mean is the thing to the left. Okay. And now what we want to be doing is to compute the U1 times U1 prime charges of states that are built like this. And as I was sketching before, for each psi I operator, let's say, that's just going to contribute whichever charge it was carrying already. So it's going to contribute Qi, say, where Qi is given here. So this is Qi tilde. Okay, so it's all very explicit. Like we just chuck in these numbers, 3, 4, 5s, and zeros. But what does the vacuum contribute? So basically, the contribution of the vacuum can be computed as a direct C So we just want to write down a sum over the direct C, which goes like this. And then just down. That's going to be over the natural numbers, plus here I use these brackets to mean the fractional part, and eta I define this guy to be eta. Well, without the 2 pi. That's eta. And then we just count all the states, and you need to do some regularization, some zeta function regularization, and find the result, which is just a function of eta, which of course has to be a half when the space is trivial. Okay, and then you sum over all the fermions, and you get out some set of numbers. And the set of numbers are these. So if we have done this right, which I believe I have since I wrote them down beforehand, then it should be possible to write down some outstate that is completely fixed by symmetry and which lives in the twisted sector of this C5 defect and conserves all the charges of the problem, conserves all the charges of these of U1 times U1 prime. And indeed, say we throw in the 3, then we can precisely solve all of these constraints at the same time by writing down the outstate as a C5 line plus an excitation of the psi5 plus the psi0. Then if we write down the U1 times U1 prime charges, this has 3.4. This line we're reading from here as -2, -1, 5, 0, 0, 5. There we go. And it all works out. And it matches the bosonic picture that we had. So basically, we've managed to solve this problem in this very, very simplified model called the 3450 model, where at first look, it looks like the only way to preserve all the symmetries of the problem is to get out this fractional fermion, whatever that is. But it turns out if you actually enlarge your Hilbert space to also include the twisted sectors of the theory, it's possible to write down an outstate where you don't have to resort to fractional fermions. You can write down a state that's perfectly integral in this twisted sector and which preserves all the symmetries of the problem. And it matches the explicit boundary conditions that you write down as Andrea was referring to in this bosonized picture. Okay, so just one more comment before we move on to monopoles. So how come people, like, where did this fractional problem go? Or how come people even thought that this was a fractional thing to begin with? So the reason for that is as follows. So say you measure the particle number. The species number. Like we want to measure a current like this. Then that is indeed going to be fractional. And the reason it's going to be fractional is because this current has a mixed anomaly with the C5 symmetry. So the U1 and U1 prime don't have any mixed anomalies. The C5 sits inside these U1 times U1 prime also doesn't have any mixed anomalies. So you can put in a boundary and preserve all of these symmetries at the same time. But the species number has a mixed anomaly with the C5, and therefore it will be broken. And when you measure it, you'll get fractional values. So because you have a mixed anomaly with the C5, then the endpoint, the vacuum state, adds a fractional amount of charge. So that's how, the whole thing fits together. Okay, so that was this story of the 3450 model. I hope I have you all convinced that this resolution works, because I'm going to be relying on it for the monopole case. I'm not going to go through all of the same detail, but the story works out very similarly. So any questions maybe at this point? Yeah.
Just a curiosity, is this the most symmetric boundary that you can define? Or you could also, because I'm thinking
Yes.
about this because in this case, the scattering is fixed by symmetries, right?
Yeah. Yes. So, and it is the most symmetric boundary. So basically it's the, so once you write down the first U1, the other, well, what do you say? It's the unique, so if you want this much symmetry, it's the largest amount of symmetry you can write down, and it's unique up to a change of basis for the fermions. So you can write down other charges and switch things around, and it might look different, but it turns out it's just a change of basis. So you just mix around the fermions and it turns out to be the same thing. So if you want this much symmetry to U1s, then it's the unique thing.
So if you take a third U1, for sure it will have either a pure anomaly or a mixed anomaly with at least one of the two U1s.
Yes.
I see.
I believe so. Well, it also just, it has to sit inside the flavor symmetry group. And so like there's just, it can only be two because it has to sit inside the left and right moving flavor symmetry.
But in principle, you have 4 U1s, right? Because you have 4 fermions. So you can assign different charges to all the fermions. You have one U1 for each fermion.
Let me see. Does the counting work out that way? I'm just right now I'm in doubt about the complex versus real fermions. If there's a factor of 2 there. Okay, sorry, I don't want to do that live. Maybe we can discuss it afterwards.
Yes.
If it's okay, Andrea.
Yeah.
Cool. Sorry.
So usually the existence of a conformal boundary condition, a symmetric conformal boundary condition, is related to existence of symmetric gap state with closed boundary conditions, not with the open breadth. So supposing you're quantizing the theory in the untwisted sector, what is the nature of the gap? Can you gap out this 3450 theory while preserving U1?
Yes. So that's so I agree. So in this context, these two statements, the fact that you can gap them out and the fact that you can put in a conformal boundary, are supposed to be equivalent, and people check this. So I know Wang and Wen checked this, and Tong and well, David and Philip also checked it, that this can indeed be done in this particular model. Yeah.
And what is the IR fixed point, the gap in that gap phase, U1 preserving gap phase? Something unconventional in some sense.
I don't recall right now off the top of my head. Sorry. Yeah,
Thanks.
I'll check it. Yeah, thank you. Okay, moving on to monopoles. So basically, there's an analogous story for massless fermions that scatter off monopoles in 3+1D QED. So if I take a TÜV line, which is, well, a probe of a monopole, a probe made out of a monopole, and then in QED, and I throw fermions at it. Kalin and Rubakov studied this problem already in the 80s. And what they observed is that even if you throw perfectly standard wave packets in, like just normal electrons, then the outgoing state can have fractional quantum numbers. Okay, so we have the same sort of problem, but in 4D, I'm throwing in some fermion here, and it scatters off the TÜV line, the monopole, which is here. And we have a question as to what comes out, because the suggestion from the 80s was that it's half an electron plus something else. And this is looking very reminiscent of what we just discussed. So in order to discuss this problem, let me just set the stage. I'm sure this audience is probably quite familiar with the construction of the construction of non-invertible symmetries in QED, but I'm going to go over it regardless. So the construction that I'm going to go over a fast version of it. So the construction that I'm going to be using is the one that was proposed by Choi, Lam, Shao, and independently Cordova and Omori. So there are also constructions which have the full U1. So here we're just going to get a discrete symmetry. But for the nature of this problem, it is in fact going to be the discrete defect that appears. So I'm just going to be using this construction because it's the relevant one. Okay, so the story is as follows. So the axial symmetry in QED called U1A in QED that suffers from an A to J anomaly. So basically we have this. The current J is not quite conserved. Rather, it has the gauge field on the right-hand side. There we go. So as I'm sure most of you are aware, that means that if I wanted to write down the usual topological operator that implements the axial symmetry, I can write that as U alpha. I write it like this, alpha star JA. Because of this anomaly, this operator is no longer topological, which means that the U1 is broken. And of course, that was the end of the story for many, many years. There's no U1 axial in QED. But it turns out, as these people showed, that you can write down a set of topological and gauge invariant operators. Which are going to be labeled by P over N in Q not set. And it's this operator. So here I'm suppressing a path integral, but it's there. It's the usual axial current. And then in order to achieve In order to cancel the anomaly, we put in a theory A n, P coupled to the background for the electromagnetic field in the bulk. Okay, so unpacking this a bit. So this operator is defined on a 3D manifold. We can call it M3. And it has this topological field theory living on it, which is a fractional quantum Hall state. That's a fractional quantum Hall state. Which is the minimal TQ of T with one-form symmetry, Cn, and an anomaly which is labeled by this P.
Hi, can I do a question?
Yeah, absolutely.
Hi. Yes. So here, so you started with this this U alpha, which is not topological, and well, there was a medium step in which you could basically redefine G by adding basically something like ADA. This Adler's modified chiral current, which is conserved. And in the articles, maybe it's not a question, I mean, maybe to you, but since you are using the construction, in the articles, they basically motivate the construction of these non-invertible operators because they say that these topological operators that are constructed with the modified current are not gauge invariant. But they are not gauge invariant only under large gauge transformations because the current is conserved. But I don't understand why we should enforce invariance under large gauge transformations because, well, these are exactly generated by, so if I have an M3 which has an S1, for example, as a cycle, then the large gauge transformation in the M3 is exactly generated by the top loop that wraps around that S1, and that is a gauge invariant operator. It generates a transformation in the M3. It exactly tells you that the top loop is mixed with this topological operator. And I don't understand why we should enforce invariance under these large transformations in order to call it a symmetry. Maybe you can.
Okay, I mean I can try to comment, but yeah, maybe I should.
It's a question that I have since long time. Maybe I mean I should, I don't know. I'm asking some people and I never get. I think it's something. I mean
you
I
wrote a
understand
paper about it too. Or maybe we can sort of. There's an interesting discussion we could have about your paper also. But maybe.
Okay. Yeah. Maybe
this is maybe not quite the right moment.
Okay. Okay.
But I agree with you. We could have this discussion later, even next week when Shuang is giving his talk.
Well, yeah, that would be. I'm sure he would be able to give more interesting comments too. Yeah.
Good. Thank you. Sorry.
Thanks. That's okay. Now, where was I? Right, it's labeled by this P. Okay, and of course, there's a coupling here. So, right, so this minimal TQ of T is coupled to the background for the one-form symmetry, and we take the background gauge field for this one-form symmetry to be the electromagnetic gauge connection. Okay, so just in case other people are not, well, completely intimately familiar with this construction, which of course also many people are, clearly Javier is, and then I'm just going to quickly write down that for p equals 1. I mean, you can write down the Lagrangian for these guys. Always, it's just a Chern-Simons theory, but it's nice and easy to do in this case, so that everybody can just see there's nothing particularly weird or exotic about this theory. It just looks like this, where this little a is a connection that lives only on the 3D defect. Okay, so it looks like that. And now what these authors showed was that indeed, if you take this topological defect and you fuse it with its time reverse, then what you get is going to be some condensation operator, and in particular, it's not going to give 1, so that this is a non-vertible symmetry. Okay, so having just quickly summarized that, I can say that the zero form symmetry of QED is given by U1 gauge. I'm going to include this for completeness times SU NF left, SU NF right, and this DPN. And this is up to some discrete identifications that I'm not going to include. So there's some C2 quotients in there. Okay, so back to monopole scattering. For this analysis, what we're going to do is we're going to work at tree level. And for now, ignore the fluctuations of the gauge field. So once you turn on the fluctuations of the gauge field, there are some subtleties that come into the picture. But we can work, well, first at tree level, and then the results that we get should be a good approximation of what happens, right? Okay, so at tree level, we can approach this problem by simply solving the equations of motion for some fermion. Called it psi, capital psi, which we're going to get the charge Q, electromagnetic charge Q, in the background of a monopole, right? So it's just a direct monopole. We just have a potential, looks like this. And I'm going to say that we have m units where m is some integer of magnetic flux. So that means if I integrate over a sphere, if I integrate the field strength over a sphere, I'm going to get 2 pi m, which is equal to Eg, where E is the electromagnetic coupling and G is, in this case, potential. Okay, so classically, what is the physics? Classically, if I start throwing electrons at a tuft line, the only thing that's going to happen is they're going to repel. So charged particles are repelled by a magnetic monopole. So they're just deflected. They gain a phase and they move away. Nothing happens. Quantum mechanically, however, that's not the end of the story. So quantum mechanically, it turns out that when you solve this problem, you can do of course, it's useful to do an angular momentum decomposition because we have spherical symmetry. And then it turns out that the lowest angular momentum mode so we can call that psi J0, where J0 is given by Qm minus 1 half. So in particular, notice that when we have a unit monopole, this is just the S wave. So in this case, we have a spherical shell collapsing in on the monopole. And rather than just picking up a phase and then moving out again, it can actually interact with the degrees of freedom at the core of the monopole. Okay. And another very, very nice feature of this problem is that, so all of the others are still just deflected, right? So higher one's deflected. But the solution to this problem for the lowest angular momentum mode turns out to show that it can actually interact with the core. And furthermore, it has a very, very nice feature, which is that infalling and outgoing motion is correlated with the handedness. So you get a chiral theory. So essentially what happens then is that the dynamics here, so the dynamics, there we go. The dynamics reduced to 2D theory. To 2D BCFT. And now you can probably start to see why I would spend all this time talking about the 3450 model before. So basically what happens is I go from the 4D theory, I get from all the left movers, from the left-handed fermions, I get a bunch of left movers in the 2D theory, where the 2D theory is defined by reducing on the sphere surrounding the monopole. Then I get a bunch of right movers, and the monopole itself corresponds to a boundary at r equals 0. Okay. So now, what are the symmetries of this 2D theory then? So in order to analyze this scattering experiment in exactly the same way as we did for the 3450 model, we need to determine the symmetries. And because the core of the monopole knows about the UV physics, it means that the symmetries that are preserved by the interactions with the monopole has to respect, well, the UV symmetries. So in particular, we can't have a 2-group. So we're going to see that the symmetry that is preserved by the monopole is the part of the full symmetry of QED, so here, which does not participate in the 2-group. And that turns out to be equivalent in the 2D theory to not having any 't Hooft anomalies and being consistent with the insertion of a boundary. So there are 2 options, as it turns out. So these are the symmetries in the 2D BCFT. Turns out that there's 2 options. There's another option here that I'm going to comment on just very briefly, or we're going to take both of them. Well, we're going to just take one of them. So first of all, the U1 gauge has to be preserved. Second of all, the flavor symmetry has participates in the 2-group, but you can either take the diagonal or the anti-diagonal, and then you get rid of the 2-group, which is why we can either have box-box or box-box bar. So both of these are options, and they're going to be realized in different scenarios depending on what your UV completion is. So the one that we're going to be discussing is the simplest case. So if you take the SU2 Georgi Glasgow model, then that's going to, in the IR, give rise to this box-box theory. But you can in principle also have the box bar. And then we're going to have SU2 rotations that are preserved. And each of these fermions are going to be sitting in the M dimensional representation, where M is the charge of the magnetic monopole. And then finally, we have this discrete symmetry, which is invertible in 2D, but it is inherited from the non-vertible symmetry in 4D. Okay. So looking at this little table, let me convince you that we have exactly the same problem as we did in the 3450 model. If I send in a psi, what comes out? Okay, obvious guess to what comes out on the other side, psi tilde, right? Send in psi, and just the corresponding right number comes out. But that's not going to work because it doesn't preserve U1 gauge. So this is no good. Now, another obvious choice or another obvious guess would be side tilde dagger. That also doesn't work for several reasons. So it doesn't work here because they sit in different representations of the flavor group. But it also doesn't work because of this symmetry, which is always going to be there, even if you only have, say, SU2 flavor symmetry. So anyway, that doesn't work either for several reasons. So this is an old problem that was studied already in the 80s, and they actually derived and wrote down for the m equals 1 case. Did I switch notation from m to n? I don't know. I do that sometimes. No, I think I stayed consistent this time. So for the unit monopole, unit charge monopole, the explicit boundary condition was written down in the 80s. So again, we can bosonize and write down completely explicitly what comes out. So really, this is abelian bosonization. So it doesn't capture the full symmetry, only the cartan. Sometimes called bosonize. But that's okay because we're going to also check the fermionic picture. But you can write down the boundary condition, which looks exactly like this. So basically, the outgoing radiation comes out in all of the channels. And for an f greater than 2, we get some fractional vertex operator. And Keller and Rubikov originally interpreted this as half electrons coming out. Of course, what I'm going to do is I'm instead going to say, I think I have a very clear analogy with the 3-4-5 picture. And my interpretation is that instead what comes out is not a local operator. When I shoot an electron at a 't Hooft line, it turns it into a defect. Okay? So we take this as the appearance of a topological line. And in particular, we can do exactly as we did before. We can compute the charges by measuring the monodromies. And we find that the line that comes out generates a set NF, which is up to a gauge transformation, just the center of the flavor symmetry. Like that. Okay, so I can see that I'm almost out of time. I think I can get it done probably in another 5 minutes or so, 10 minutes maybe. Okay. Good. Okay. So what does this process look like in the fermionic picture then? So again, we can look in the fermionic picture. And we can compute the charges in twisted sectors, just like we did for the 3450 model. So there's some general formula again you can write. Vacuum charge of this T to the K, where T generates that NF. Which is given this. And is computed in precisely the same manner as before. using this direct C and some regularization scheme. And then you find that you can write down a process sending in at psi I, and what comes out, which is consistent with all the symmetries, is this t to the -2 plus the right moving counterpart. And then I have an incoming fermion that has electromagnetic charge +1. If you compute the vacuum charge of this t to the -2 line operator, then you find that it is +2, and this one has -1. So it works out. And similarly, you can check for all of the other symmetries that I wrote down that this scattering preserves all of the symmetries and transforms in the right representations. And at the same time, it is completely consistent with this. So it's the same thing, just written in bosonic language or in fermionic language. But whereas the bosonic language only captures the Catan, we capture the full symmetry here in the fermionic language. Okay, so finally, the punchline, the uplift to 40, and the higher charge monopoles. So for higher charge monopoles, so we have m greater than 1. Instead of generating just a set NF, we find a topological line which generates set M. There we go. And this set M and F is, let's see, acts on the fermions like this. And same for psi tilde. So it acts the same on both of them. Like that. And simply by this action on the fermions, you can uplift to 40. And see that this line defect in 2D has to uplift to this non-vertical symmetry defect. Okay, so uplifting it to 40, I get a 3D surface. And the action on the fermions is such that this 3D surface has to be d2 over m. And d2 over m, we see is non-vertical for m greater than 2, actually. Okay. So, oh, this picture belongs up here. This one. So this is the punchline. This is the punchline. So basically, this puzzle that was discovered by Kellen and Rubakov in the 80s, you can solve the problem in 2D by proposing that what comes out, rather than being some kind of fractional fermion state, what comes out is a line defect, which has some excitation living at the end of it. The thing is, even if Kellen and Rubakov had gotten this far back in the 80s, they would have been at a loss for what happens in 40, right? So this is the reason why this problem has, only just, well, the solution why that has only just been possible to propose is because since we had absolutely no idea about generalized symmetries 10 years ago, definitely not in the 80s, and we didn't understand that this particular non-vertical symmetry of QED even existed until, a couple of years ago, 2021, I believe. So even if you had proposed to include the twisted sector in the 2D picture, you would have been forced to say, okay, but it doesn't make any sense in 40, right? But thankfully, the whole situation has resolved itself because we now understand the existence of these symmetries. And well, our proposal for this scattering experiment is you throw in some left-moving fermion, and a twelfth line or a monopole converts this into a topological defect with a right-moving excitation living at the end of it, and some topological field theory living on the defect, which makes it non-vertical. That's it. Thank you.
So thank you very much, Marieke. That was a very pedagogical talk. Are there any questions for Marieke?
Sorry, there is a point which is slightly confusing for me at the end. I mean, the fermion is actually a local operator, right? So here you're putting it at the end of the 3D topological operator only because you are in the S waves, right? Correct?
That's right. That's exactly right. Yeah. Yes. So the point you're making, yeah. So the point you're making is that that there's tension with the dimensionality there. So basically, the way this computation works is, as I stressed, is that we're doing it in an approximation where we're not really considering fluctuations of the gauge field. So what that means is that it's only this lowest angular momentum mode that even interacts with the monopole. So the picture we have is you throw in a localized particle, and you decompose that into angular momentum states, and and you decompose that, and it turns out that only one component actually interacts with the monopole, and that's the thing that we're saying is attached to a shell, right? And well, is attached to a defect, which makes sense because it's a shell. But now you would want to, of course, put all of these momentum modes back together and say, okay, it's an electron. If I try to measure it, it's going to come out as a point thing. And I understand that tension. I think it should in some way or another be resolved, or there should be an explanation if you figure out what happens beyond tree level, because then it necessarily also has to involve the higher momentum modes. And I think there's some way to, there must be some way to interpret this if you understand how they also interact.
I see. Even if you think about it from the point of view of states in the Hilbert space, in the 2D picture, you were talking about states in the twisted sector. So you have like the Hilbert space twisted by the line, and so you have in the twisted sector you have particle states. Now if you want to take this picture in this 4-dimensional case, you are talking about the twisted sector of a zero form symmetry. So the states in this twisted sector will not be particle states, will be like membrane states. So it seems like that there is an effective description for the S waves in which from the electrons you can get membrane states. So it's a bit confusing for me.
Yes. Yeah, I take the point. It is a bit confusing. I don't know what happens beyond this picture, but yeah, I mean the picture we have is only of the S wave, and yeah, of course that's not the same as an electron, but this is the thing that it makes sense to say could possibly live in the twisted space of this defect. Yeah.
I see.
Thanks, Andrea.
Thank you.
More questions? Okay, if not, let's stop the recording and thank Marieke.